All right, how many points do you need to define a curve? So to define a straight line, you only need 2 points, but to define a curve, you would need 3 points minimum, right? The more, the better. But there's always a danger. If you have 3 points and they're experimental, then you have normal experimental error or random error that fluctuates. And so sometimes you take 3 points like this to define a curve, and because of the experimental error, it could just so happen to be straight when it's actually a curve or whatever else. And so if you take 3 points, you want 3 points widely spaced apart. So for example, a point here and a point here, and maybe a point down here later on. And so let's take on 3 points and see if we can figure this out. So maybe we'll go, we'll spread the points out a little bit rather than, let's say we had a data table that looked something like this. So in this example, we're going to do this. What if we can't graph it? Then we will use what I call slope, or K analysis. And so we need 3 points at minimum. But 3 points is dangerous, right? Because of any kind of experimental error. So typically we want more than 3 points. The more points, the better. So this is 3 points minimum. The more, the better. But all we really need are just 3. And then the way we can visualize what we're doing here is like this. If we look at the concentration of A versus T, if this is linear, then it's 0 order. So we take a look at point 1, point 2, and then point 3, like this. And of course, the tighter in their space, the more potential there is for error. And the further out their space, the less. So if I put in 3 tightly spaced points, does that look like a curve to you? And what kind of curve does that look like? And so this is a little bit dangerous, And so the further out their space, then you can see, like say for example here, the further out their space, then you can see if it's linear or if it's curved. Because if this were linear, then the next point should lay about here. But if this were curved, then the next point might be out here. And so the further out, this is better. Maybe this is okay, but this is not so good. Because when you get tightly spaced points like that, it always looks linear. 3 tightly spaced points. But in this, we look at the slope of each segment. And so between the first point and the second point, we're going to generate a slope, this. And between the second point and the third point, we'll generate another slope, here. And then what we just do is we compare the 2 slopes. If it's linear, the 2 slopes should be the same. And so we compare the 2 slopes. i.e. we calculate the percent difference. The percent difference is the biggest slope minus the smallest divided by the smallest, times 100%. So compare the 2 slopes. We're going to do this for the 3 plots. So we'll generate the A versus T plot. Actually, we aren't even going to generate the plot. We don't have to generate the plot. I mean, there are only 3 dots there. So we're going to do it a different way. We're going to look at the ln of A versus T. the ln of A, we're going to get 3 data points here, and then we'll just compare, the slope again. The slope of the first segment here compared to the slope of the second segment here. And then finally the 1 over A. All right, the slope in each of these 3 plots is related to K. So let's take a look at the relationship between the slope and the K. It's related to K by looking at the integrated rate law. The integrated rate law here is the concentration of A at time t is equal to K minus KT plus the concentration of A at time 0. And so we see here, this is just y is equal to mx plus b. This is why the earlier plots work. And therefore the slope, m, is just equal to minus k. Or k is equal to the negative of the slope. And so rather than calculating the slope, it's much easier just to calculate the k value, or at least just the same. And so what we're going to do is we're going to compare, instead of comparing the 2 slopes, we're going to compare the 2 k's. And so we'll call this K for segment 1. K1 is equal to, we're going to solve this equation for K1. And that's just going to be A at time t minus A at time initial. I'm not going to call it 0 because sometimes we don't start at 0. Over t, the time interval. The time interval is actually delta t, which is t final minus t initial. So we'll just call the time interval or delta t. The reason I'm not just going to call it t final is because t initial might not be 0. And so we're going to compare K1 to K2. K2 is the same thing, it just has a different initial and different final. It might have a different time interval too. Over here, when I calculate the K, the equation for K is going to equal this, because I know the integrated rate law is ln of A at time t over A at time 0 is equal to minus KT. That's given, and therefore K is equal to minus ln of A at time t over A at time initial rather than 0, because it doesn't have to start at 0, over the time interval. And then over here, I'm going to get K is equal to 1 over A at time t minus 1 over A initial divided by the time interval. This comes from an integrated rate law. The integrated rate law for this is 1 over A at time t is equal to plus KT plus 1 over A at time 0. And so we're going to calculate the K's instead. And so let's pick 3 data points. Here. And so I look at this first experiment here. I have 3 data points. So I should be able to figure out if this were 0 first or second order by either graphing it. Well, I don't have access to graphing software, so I'll just do it by hand. Graphing by hand is subject to error, so I'm just going to do a K analysis. So let's do this. I mean, can you eyeball it and tell me? Is this 0 first or second order? No, I don't know. So let's make up the tables. The table's going to look like this. We'll put the time on the left here. So the time is going to be in minutes. So 0, 1.0, 2.0. And then the concentration will be a molar. It will be 1.5, 1.2, 1.490, and 1.469. and we want to figure out what order is this. This is just A goes to product. It's a simple decomposition reaction. And so what is the order? Not only can we find the order, but we can get the entire rate law. The rate law will need the order, that is, is it first order, second order, third order, and we'll need K. And so the rate law is going to equal Ka to the n. And so the first thing we'll do is we'll try zero order. Is it zero order? Well, solving for K for zero order, it's going to be A times T minus A initial divided by the time interval. And so we're going to go with segment 1 here. We're going to call this K1. And then this second one here we'll call K2. Yes. So the slope, or K between these 2 points, between those 2 points. So K1 is going to equal A times T. A times T is 1.490 minus A initial, which is 1.512, divided by the time interval. The time interval in this case is 1.0 minutes. And so this is going to, the units here are going to be molar minutes to the minus 1, or molar per minute. So what does this come out to? 22. Okay, 0.022 molar per minute. Okay, that's for the first segment. All right, then let's take a look at the second segment, that is K2. So this will be my final, that would be my initial. And the time interval would be 1 again. And so this is going to be 1.469. Oh, there's a negative here, sorry. 1.469 minus 1.490 divided by the time interval, delta T, which is 1.0. Again, the same units molar, minutes to the minus 1. And so 90 from 69 would be 31.031. All right, now, if this were linear, then the 2 slopes should be the same, right? 2 slopes, but looking at it, those 2 slopes don't look the same, do they? No. So we'll take a look at the percent difference. The percent difference is going to be the biggest, 31, minus the smallest, 22, divided by the smallest, 22. Equals 9 over 22, which is equal to what? I just moved the decimal place over. 40.9%. So the 2 slopes are quite a bit different, actually. Did the math correct? All right. So that's zero order. Now let's assume it's a first order and see. If we assume it's first order, then K is equal to ln of A times T over A initial divided by the time interval. There should be a negative here. So let's look at the first segment. K for segment 1 is going to be the natural log of 1.490 over 1.512, and the time interval is 1.0 minutes. Can somebody calculate that? .016. 0.01. The units are different here. The units are going to be minutes to the minus 1. That's it. The units are going to be different because of the rate law. If I go back to zero order, the units for zero order are going to be on K are going to be molar per minute. That's because M is equal to 0, and so there are no units here. And so the rate should be in molar per minute in this particular case. For first order, M is equal to 1. Therefore, the units concentration of A will give us molar. Therefore, K is per minute. So this gives us molar per minute. And so the units are different depending on what the order is. So this is going to be minus ln for this next segment, 1.469 divided by 1.490 divided by the time interval, which is 1.0 minutes. Put parentheses there. And this gives us what? .0141. So let's calculate the percent difference. I'll take the biggest 146 minus the smallest 141 divided by 141 percent. Or I don't have to move the decimal. I just move the decimal for leave it at 0.0. 3.54%. Better, but you know the best would be if there's 0% difference, right? Because then we know, yeah, it's truly linear. So let's see what second order gives us next. If we go to the second order, then K is equal to 1 over A times T minus 1 over A times 0 divided by the time interval. So you'll need the invert key on your calculator. So we're going to have 1 over 1.490 minus 1 over 1.512 divided by the time interval. Time interval here is only 1.0 seconds or minutes. And so the units are here are different. It's going to be molars to the minus 1, minutes to the minus 1. And that's because if it's second order, M is equal to 2, which means we're going to have molar squared. The rate should be molar. And so we need to cancel out one of those. And the way we cancel out is with K. K cancels out one of those and then adds the per minute. And so what does this one come out to? So the way you punch this is 1.49 invert minus 1.512 invert equals divided by 1. You don't have to do divided by 1 though. 0.0097? 6. Okay. And then let's go to the next segment, K2, which is going to be 1 over 1.469 minus 1 over 1.490. And the time interval for this is 2 to 1, so it's just 1 second, or 1 minute, sorry. Units are the same, molars to minus 1, minutes to minus 1, which gives us 0.00959. You leave the decimal the same. So the percent difference here is 976 minus 959 divided by 959 times 100%. .7? 1.7%. All right, so the most linear of the three looks to be the second order. But 1.7 is close to 2. A difference between 2% and 3%, is that all that big? No. And so it depends on how much experimental error we had, you know. I would still worry, but given the data we have, the best fit would be second order. And so, therefore, M is equal to 2. So we figured out what M is, then we have to figure out what K is. And so the K is, the best is to get the average K. Both K's should be the same, right? It should be linear. But both K's should be the same, so we'll just take K1 plus K2 divided by 2. So 959, 976, what's the average of that? 0.00.967. Okay, the units here are going to be molar to the -1, minutes to the -1. And so what we're going to end up with is the rate law. The rate law is going to look like this. The rate is equal to K, which is 0. I'll just write it out first. Is equal to K A to the M. We know what K is. It's 0.00967 molar to the -1, minutes to the -1. And we know what M is. M is 2. Okay, so this would be the rate law. The rate law will allow us to predict the rate at any concentration. It allows us to predict what happens if we double the concentration. If we double the concentration, the rate should quadruple.
Will it have an effect if it's 0.035 for the first K? They got it with me, honestly. I didn't get the 0.09.
Yeah, it would make a difference. What did you get?
Not 0.035 here.
This one?
Yeah.
0.035? Well, let's do it again. Just double check it. So I would punch in 1.49 invert minus 1.512 invert equals. You don't need parentheses. 0.035. All right, let's 0.035 what? 350? How about this one? That one's right?
512 or 517?
512. Sorry.
Never mind, that's right. Yeah, because it was,
Well, actually, here's the original data, 512.
Oh, yeah, then that was right.
It was right?
Yeah.
Oh. 976? All right, sorry. It was just this, 512. Okay. So are we still good with the calculations? So this one appears to be the most linear, so we're going to say second order. This would be the rate law here. From the rate law, we can also get the integrated rate law. If this is second order, you know, if we want to figure out how much and how long, we need the integrated rate law. the integrated rate law is going to be 1 over the concentration of A at time t is equal to plus kT. So this is going to be 0.00967 molar to the minus 1 minutes to the minus 1 times t plus 1 over A at time 0. And so the integrated rate law, we can get how much, which would be A at time t, and how long, you know, the time interval it takes. How long. Whereas the rate law, you know, doesn't really tell us much other than if I double the concentration, the rate should quadruple. If I cut the concentration in half, it should slow down by fourfold. The integrated rate law is much more useful for our calculations. That's what we got here. All right, so that's an alternative to graphing. If you have a lot of points, then you don't want to do this. You know, because if you got a lot of points, you know, that's a lot of segments. So, you know, we calculate K, the segment 1 here, segment 2, segment 3, segment 4, segment 5, segment 6, segment 7. So doing this for 7 different segments here would be quite a pain. Not only that, you know, there's actually more because you can jump in between points here. So this is much easier. If you got a lot of data, you might as well just graph it or try to graph it. All right, are there any questions on this? This is how you do it without graphing. You could just look at K. K should be constant. All right. When we have multiple reactants, will complicate the kinetics. And so, for example, if I have a, let's just look at this earlier. If I have this set up in A, where we have A plus B, now we have 2 reactants. The overall rate of the reaction is going to depend on both A and B. So just as a refresher, you know, if we kept A constant and we doubled B, we saw the rate quadrupled. So it was second order in B. And then if we keep B constant between 1 and 3 here and double A between 1 and 3, the rate doubled. So it's first order in A, second order in B. But what happens is, you know, when A changes, B is going to change too. So if we double both A and B, then we have 1 and 4, and the rate went up 8-fold. So it's third order overall. And so the overall rate, you know, the rate that's going to be observed is going to depend on both the impact that we see from A and the impact we see from B. And so, in other words, what happens is this. If we start off with 1 molar A, and we consume half of it, and we start off with 1 molar B, how much have we consumed of the B? So 1 molar, minus 0.5 molar, this is going to be minus 0.5 molar. It's a 1-to-1 mole ratio. And so that means if A gets cut in half, B gets cut in half, and the net impact is we're going to see not 1/2 the reaction rate, not 1/4, but 1/8 the reaction rate because of the third order dependence. And so it gets complicated. So when we have multiple reactants like this, you know, let's say we have an A plus B yields a product, then the rate that's observed is going to depend on both A and B. And so this is going to be M, B to the N. And so we're going to see the overall order of the reaction is equal to M plus N. Therefore, let's say the overall order, let's say we cut A in half and B in half, and the overall order was 3. So in this example, let's say the overall order equals 3. then we have different possibilities. The possibilities are maybe it's third order in M and 0 order, right? Or maybe M is equal to 2 and N is equal to 1, right? Or maybe M is equal to 1 and N is equal to 2. Or maybe M is equal to 0 and M is equal to 3. N is equal to 3. You know, so which is it? Yeah. Which is it? We don't know. Therefore, we do this. We do what we call the method of initial rates. That is, hold one of them constant. And then change the other, and see what impact. And then switch. And that way we can figure it out, what the order is. And so the easiest way to determine it is the method of initial rates. Why the initial rate? Because that's where we know what the concentrations are. The initial rate is the rate at time 0. At time 0, we have the initial concentration. After 5 seconds, let's say this reaction's gone for 5 seconds, do you know what the concentrations are? No, because both of them are being consumed. They change. It depends on how fast they change. So we don't know. Well, necessarily what they are. And so that's fine. We could use the method of initial rates, just like in problem number 11 here, and figure it out. But let's try that in our reaction. We did crystal violet plus hydroxide. This yields crystal violet hydroxide. So this is an A plus B yields product. And so we have 2. Reactants. And so what we did was we made some plots up. We did the concentration of crystal violet versus time. When we look at the concentration of crystal violet versus time, then it was a curve, right? And we took a look at this curve. Then we tried to fit this curve with a linear trend line. Here, so the blue is my data, the black is the linear trend line I'm trying to fit it. And so this is the best straight line I can draw through my data. Does it look like a good match? No, this looks pretty nonlinear. And we can see it's not a good match by the R squared. Take a look at the R squared, it's 0.949. Is that a good R squared? No, not good. So 0.94. All right, then we plotted our natural log versus time. And we have the blue data, and we have the black, and that looks like a good fit. A lot of the blue dots line up with the black line. And we can see this by looking at the R squared. The R squared is much better. We got 3 nines now, 0.9997. So that looks good. A perfect fit, that is, if all the blue dots line exactly on the black line, then the R squared would be 1. And so let's see what the 1/8 plot looks like. If we look at the 1/A or 1 concentration, it's pretty nonlinear. If you try to fit that to a straight line, it doesn't look so good, and we can see that in the R squared is only 0.94. And so this looks to be what order? If the concentration versus time is linear, it's 0 order. The rate doesn't change. if the ln of A versus time, yeah, is linear, then it is first order. And so we see that, yeah, we tried to fit this doesn't look good. We went on to this one, the ln of the concentration of CV plus versus time, and this looked good. This looked pretty linear.
That's the first order.
Yeah, this would be first order.
But I thought zero order was
Zero order was decreasing? Zero order would look like this. If this were zero order, then the rate is constant. That is, the slope doesn't change. So the slope stays constant.
I thought that was for first order.
No, because here, it's going to be like this, because the rate is equal to Ka to the zeroth. And so as the concentration of A changes, does that have any impact on the rate? No, it doesn't, because A to the zeroth is just 1, and therefore it's K rate. Whereas here, the rate, when we look at this curve here, you know, the rate is equal to K times the concentration of CV to the first. That means as the concentration gets cut in half, the slope gets cut in half too. And so 1/2 the concentration was 1/2 to the first power, so 1/2 the slope. And so this would be a first order. One way to do that is to use the integrated rate law. If we use the integrated rate law for, did I write these up? For first order, the integrated rate law is the ln of CV plus, I'm going to rearrange that equation, at time t is equal to minus kt plus ln of CV plus initial, or time 0. And so if it is first order, then we're going to get this as being linear. A plot of the natural log of the crystal violet concentration versus T should be linear. Did I talk about this already? Yeah. I think so. All right, and then the last plot, which is 1 over the crystal violet concentration versus T, came out nonlinear here as well. All right, run 2 should verify this as well. So when we look at run 2, I'll put the natural log plot at the top here. You can see 3 9s, looks pretty good. The concentration versus time, 0.95. And 1 over the concentration versus time is 0.93. That's the R squared. And so those aren't linear. And so both run 1 and run 2 confirm that it's first order in crystal violet. But there's a problem. What about the hydroxide? Does the hydroxide have no impact? If I consume half my crystal violet, how much hydroxide have I just consumed? Let's say I started 1 molar here, 1 molar here. If I consume half my crystal violet, then I must have consumed half my hydroxide. And so what I'm observing here is I'm observing the overall order. The overall order is first order. If the overall order is first order, then I have some possibilities. The rate is equal to K times the crystal violet concentration to the M times the hydroxide ion concentration to the N. We don't know. Maybe the hydroxide has no impact on this. If hydroxide has no impact on this, then N is 0 and M is 1. But what if hydroxide did have an impact on this? Then we have other choices, right? maybe what we're observing here is it could have been 0 order in crystal violet. It could care less how much crystal violet had, and it was 1st order in hydroxide. And it just so happened as the crystal violet was being consumed, the hydroxide is being consumed at the exact same rate. It's a 1-to-1 mole ratio. And so the problem here is we don't know. Is it 1 and 0? This could be 1, 0, or is it 0, 1, or etc. Right? Because what we observe is the overall order.
So it's never done in fractions.
It could be fractions too, like 1/2 order. That's possible. And so it's the same thing here. You know, this just so happened that we held one of these the same. But if we allow both of them to change, you can see both of them changed and it caused an 8-fold increase in the rate. So then it's easy, because what we're seeing is we're seeing an impact on both. Both crystal violet and hydroxide are changing. This is what's happening. So all we have to do is hold one constant and then change the other, right? But there's a problem here, because this is the method of initial rates. That's, you know, the tangent at time 0. When you did your reaction start? When was the time 0 on your reaction? When you mix the crystal violet with the hydroxide. That's time 0, right? And then there's a big problem, because did you take any measurements at time 0? No. In fact, well, if we don't have the tangent at time 0, we could use the first 5% of reaction and take the average rate. Did you get data from the first 5% of the reaction? No. By the time you mixed it and filled the cuvette and then put the cuvette into the spectrometer, do you know what the precise concentrations of both crystal violet and hydroxide were? No. And so you know what? The method of initial rates is impossible for us, because we have no data at the beginning, and the only point where we know what the concentrations are is right at the beginning, because once the reaction starts, concentrations are going down, right? And we didn't measure the concentrations. Well, or we didn't. We didn't measure. We could, I guess, with the absorbance, but the hydroxide we didn't. So we have a problem, and so this is what we do. For us, the method of initial rates isn't going to work. So the easiest, of course, would be the method of initial rates. But the problem is we have no initial rates. No initial rates were measured. So we use another method. And the other method is called, at least for crystal violet, we're going to use a hybrid of methods. The first method is what we call pseudo M order. What we did was we made the reaction pseudo M order. How do you make a reaction pseudo M order? The way we make a reaction pseudo M order is like this. if I have a rate law that's rate is equal to K, A to the M, B to the N, dot, 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 I make this one, or these ones, make these concentrations very large so that they are essentially constant over the course of reaction. Over the course of reaction. Then if these are a constant or relatively constant, then what I'm going to do is I'm going to combine these two constants here and here into one constant called K prime. And therefore this is only going to depend on the concentration A, because if the concentration of B and C and whatever else is in there doesn't really change, then that's not going to have any impact on the rate. This is called pseudo M order. So let's take a look at our data here. All right, well, does anybody know the crystal violet concentration that we use? Okay, this is from a different year, so I need to change this. 0.01593. Okay. So the standard is 0.01593. So I changed that concentration. That's in grams per liter. I don't want that. I want it in molarity. And so I have the molar mass I calculated down here, 408. And so if I take the grams divided by the molar mass, I'll get moles. It'll give me moles per liter. And so when I look at the crystal violet standard, the concentration is 3.9 times 10 to the minus 5 molar. 3.904 sig pigs. That's 39 micromolar. 39 micromolar, is that very concentrated? Not extremely dilute, but the color was very intense. Things that have very intense color have what we call high extinction coefficients or high molar absorptivities. They absorb a lot of light and are intensely colored. And so crystal violet is one of those. The extinction coefficient, I think, was like 87,000. All right. What was the molarity of the sodium hydroxide standard that we used? I know what it is. It's 0.1016. You don't have to look it up again. 0.1016 molar. All right. Then we did our solution dilutions next. In run 1, we did a 15 DI water, 5 sodium hydroxide, 10 CV, right? And so we need to get the initial diluted concentrations. Step I is solution dilution. And so the hydroxide is a 5 to 30 dilution. So 5 to 30 dilution of 0.1016 comes out to 0.0169. And then the crystal violet is a 10 to 30 dilution, which comes out to 1.3 times 10 to the minus 5. Now, we aren't starting, even though they react in a 1-to-1 mole ratio, we aren't starting. We have a large excess of what? These react in a 1-to-1 mole ratio. We have a large excess of sodium hydroxide. There's a large excess of hydroxide here. In fact, if you look at it, the crystal violet is about 13 micromolar. This is a lot more. This is about 1,000 times more. And so in other words, we have 1,000 times more hydroxide than crystal violet, even though it's a 1-to-1, so we have a huge excess of hydroxide. All right, so what we want to do in order to figure out what M is we want to make this reaction pseudo-M order. To make it, we need to make the hydroxide very large. If the hydroxide is very large, then it doesn't change much over the course of the reaction. Well, let's see how much the hydroxide would change over the course of the reaction. So here's a calculation showing that. Here, the initial crystal violet is about 13 micromolar. The initial hydroxide is about 16 millimolar. So 1,000 times more hydroxide. They react in a 1-to-1 mole ratio. So what we're going to do is we're going to assume, let's say 90% reaction of the crystal violet. So this would be minus 0.9 of the initial. We're going to end up with 10% left. That is 0.1 times initial left. And so when we have 90% of the crystal violet consumed, how much of the hydroxide do we consume? So here's our initial hydroxide. It reacts in a 1-to-1 mole ratio. So if I lose 1.17 times 10 minus 5 crystal violet, I'm going to lose the same in hydroxide, 1.17 times 10 minus 5. Well, if I lose that much from this initial, I'm going to end up with 0.0169216. So I go from 169,333 to 169,216. Was that a significant change? So I calculate the percent reaction of the hydroxide. It only comes out to 0.069%. Did much hydroxide react? That's less than 0.1% of hydroxide reacted when 90% of the crystal violet reacted. And so what that means is this. As the crystal violet's being consumed, that's going to have an impact on the rate, right? During that whole time, the hydroxide barely changed. And therefore, the hydroxide was fairly constant throughout that whole, it did change a tiny bit, but we're going to ignore that change, right? It's going to lead to an error, but we'll ignore it. And so essentially, the curve that we see comes from crystal violet. And so we go back to this. By making this pseudo-M order, then the only thing affecting or impacting this is the crystal violet. The hydroxide didn't really change, so the hydroxide is not going to impact the rate of the reaction. Therefore, we know that it's got to be first order in crystal violet. Hydroxide didn't change. Okay, the same thing happened in run 2. If we look at run 2, we're going to do the same thing. We're going to consume 90% of the crystal violet. How much of the hydroxide did we consume? Well, in here we had twice or double the concentration of hydroxide, so the percent's even smaller. It's half the percentage. We only consumed 0.03% of the hydroxide. And so we have a huge excess of hydroxide, therefore it didn't really change. And so in run 2, what's impacting the rate is only the decrease in the crystal violet here, concentration. The hydroxide has no impact on this. Does that make sense? And therefore, we made this pseudo-M order. That is, hydroxide is at such a high concentration, we'll just combine the constants and call it K prime. And so to determine M, we make the rate law pseudo-M order. This is done by keeping the hydroxide very high so that it remains essentially constant through the course of reaction. We can show this by calculation. That was a calculation we just showed there. All right, so now we know what M is. M is 1 because the ln plot came out linear. Run 1 and run 2 showed the same thing. It's first order in crystal violet concentration. Did hydroxide impact the rate at all? So for example, between run 1 and run 2, what did you do? You doubled the hydroxide. When you doubled the hydroxide, did the rate change at all? Did it go faster, slower, or stayed the same roughly? Went a little bit slower. Run 2 was a little bit slower than run 1. Yeah. 3 more minutes. Well, let's take a look at this data here. This was run 1. This one took, let's say, about 50 minutes or so. If we look at run 2, run 2 was a lot faster. And so hydroxide has an impact. So how can we figure out hydroxide order? So think about that for a minute.
Oh, I know what you do. You have a window and then you put your hair out and you brush it and you're like, that's what you do. That's why you have long hair. I wish I had more. I know, you just put your hair out the window. Doesn't it get annoying when you have to put your hair out the window? Because you have a good hair with it's just so great. Everyone's so cool. The flowers and it's so detailed. Every find no flowers, but yeah. Are you gonna donate your hair or no? You're gonna let it grow? Donate it.
So did you come up with an idea for figuring out the hydroxide? That's one possibility. Another possibility is rather than making it pseudo M order, we could make it pseudo N order. We could make it pseudo N order by increasing the crystal violet. So we make the hydroxide concentration small, and then we have the crystal violet like 1,000 times more concentrated. But there's a problem with that. The problem is how are we going to monitor the experiment? If the crystal violet concentration doesn't change significantly over the course of the reaction, then will the color change? The color won't change, and therefore the absorbance won't change. And so we can't use a spectrophotometer or spectrometer to monitor the reaction. But we could use what instead? Because the color is going to stay the same. It's the hydroxide that's changing. How can we monitor the hydroxide? Hydroxide's colorless. Is there a way to monitor the hydroxide? pH meter. So what we could have done is we could have just put a pH meter in the beaker or something. We can't fit it into a cuvette, but we could do it in the beaker. If we put a pH meter in the beaker, then we can monitor the pH change over time and then use that as an indication of the hydroxide. But are pH measurements easy? No, I mean there's concentration gradients and there's lag, and pH meters aren't so responsive, as quick or as rapid as you'd like them to be. And plus, we don't want to have to hassle with setting up a pH meter. And so that we could do it, it's just a lot more work, and we didn't do it. And so what else could we do then? Well, we could try the method of initial rates, but we can't do the method of initial rates because we don't have the initial rate. And so what we're going to do is we're going to do a modified method of initial rate. In this particular experiment. The modified method of initial rate, because we don't have the initial rate, well, it turns out we don't need the initial rate. Let's take a look at the math that's involved here. Because we're doing it pseudo M order. Since we're doing it pseudo M order, we have some additional data that we could use. And so that is, rate 2 is actually faster than rate 1, because there's a higher concentration of hydroxide. And so when we do rate 2 over rate 1, rate 2 is going to equal K times the crystal violet concentration 2 to the M times the hydroxide to the N. And so we know that hydroxide does have an impact on the rate because we could see it in the graphs. Hydroxide, if the concentration does change, the rate does change. The rate 1 is equal to the crystal violet concentration 1 to the M times the hydroxide concentration to 1. I'm sorry, this both should be 2 on top and 1 on the bottom.
Could you then plug in the concentrations?
Well, we could do that, but we aren't going to do that yet because we don't have these. We didn't measure the rates. And so these are missing, the initial rates. And so what we're going to do now is in run 2, we made the hydroxide huge. And therefore, I'm going to take the hydroxide and combine constants and call it K prime. This is where K prime is equal to K times the hydroxide of run 2 raised to the nth power. And this is going to be times the CV plus concentration to the M. Okay, this I'm going to repeat down here because we have a hydroxide here. But the hydroxide is a different concentration in these 2 runs. And that's going to give us a different K prime because this had a lower hydroxide, this had a higher. So we're going to call this K prime 2, we're going to call this K prime 1. Whereas over here, the K's are actually the same, it's the same reaction, but the K primes these are called pseudo rate constants. The pseudo rate constants are different because they're going to depend on the concentration of hydroxide that are incorporated in there. Times the crystal violet 1 to the M. Now we're going to simplify these equations here. In the first equation, the K's are the same reaction. What was the initial crystal violet in run 2? There, the initial crystal violet in run 1 is the same, so those cancel. The hydroxides were different. Over here, they're the same. So we actually don't need this. We don't need what we need is this. We need the K primes. And let me talk about where we're going to get the K primes from. But let's simplify this further. And so this is going to simplify into the hydroxide in run 2 to the N over the hydroxide in run 1 to the N is equal to K2 prime over K1 prime. Well, I know that the hydroxide in run 2 was double the hydroxide in run 1. And so the hydroxide in run 2 is equal to 2 times the hydroxide in run 1. That's going to be to the N. And then we have the hydroxide in run 1 to the N is equal to K prime 2 over K prime 1. And then the hydroxides to the nth will cancel. This hydroxide cancel that hydroxide. And so we end up with this. 2 to the n is equal to k2 prime over k1 prime. Now where do we get k2 prime and k1 prime from? Those are going to come from the pseudo n graphs. And so we know that run 1, the ln of A, or the ln of crystal violet versus time was the most linear. All right, we ran this at a very high hydroxide concentration. And so the equation for this line is that the ln of the crystal violet concentration at time t is equal to minus kt plus ln of the crystal violet concentration at time 0. This k, because the hydroxide concentration was so high, this k is actually equal to k1 prime. And so this is y is equal to mx plus b, and therefore the slope here is minus k. Or k is the negative of the slope. K prime is. So what we did was we wrote the equation on our graph. So this, if I just change the sign here, the slope is my k prime. And so when I look at this, this is run 2. I look at the slope, it's 0.1324. Then I go to run 1. Run 1 was slower. And run 1 was slower, the slope is less. The slope is from negative 0.04487, therefore k is 0.04487. And so k prime just comes from the slope. And so let's plug those in here. So rather than taking a ratio of the initial rates, I'm taking a ratio of the pseudo rate constant, the pseudo m order rate constant. And so I get 2 to the n is equal to k prime 2. The slope for is 0.13245 over k prime 1, which is 0.044789. So taking a look, I doubled the hydroxide. Did the rate constant double? If I double the hydroxide and the rate constant double, then it's first order. If I double the hydroxide and the rate constant quadruple, then it's second order. So did it double or did it quadruple? Well, go ahead and take this 0.13245 divided by 0.044789 gives us 2.95. So almost 3. So the hydroxide was double, and so we got to see the impact. We doubled the hydroxide. If n is equal to 1, it should have doubled, so it should be 2. If n is equal to 2, it should quadruple. It's halfway between, right? And so what should I do? Well, the problem here is this. This doesn't come out so clean. What happened is I doubled the hydroxide and it went up threefold. And so what is the order of that? And so sometimes with the experimental data is not so clean. And so this gives us trouble. And so the best thing is not to eyeball this. The best thing is just to go ahead and calculate it. And so to calculate this, we'll take the natural log of both sides. So we'll get ln of 2 to the n is equal to ln 2.95. And then drop the n in front. So we'll get ln of 2 is equal to ln of 2.95, which means that n is equal to ln of 2.95 divided by ln of 2, which comes out to what order? 1.56 order. So it's 1.56 order, so that means I probably should round that up, right? I should round that up to 2. What do you think? Or should I round it down to 1? No, I should do, unfortunately, it's a coin toss. Is it first order? No, is it second? I don't know. Maybe if I round this up, it's second order. If I round it down, it's first order. So what order is it? Well, unfortunately, our data gives us this. And so it's 1.56 order. Well, what does 1.56 order mean? Oh no, but it's 1.56 order from our data. And so I see it's going to be 1.56 order in hydroxide. That means if I double the hydroxide, then the rate should increase threefold, right? And so this is what we have so far. We have that the rate is equal to K times the crystal violet to the first, and then the hydroxide to the 1.56. What is K? Now K is not the pseudo rate constant, K is the rate constant. And so from run 1, we can calculate K. K is going to equal K prime 1 divided by the hydroxide from 1 to the 1.56 power. And from run 2, K is equal to K2 prime divided by the hydroxide from run 2 to 1.56 power. And so that's what I did here. I took the pseudo rate constants and got the regular rate constants. Rate constants should be the same for both. And so what I'll do is just average it. And so the best is just to average these two K's. So this is going to equal the average K. That is K from run 1 and K from run 2. Mm-hmm.
So on the previous graph, you said that it was the overall rate, right? Instead of this first order. How does that work?
All right. On the previous graph, I said overall it's first order. Overall it's first order, but it's 1.56 order in B. And so overall it's 2.56 order overall. And so I should see that here. The reason I don't see that here is because even though as the concentration of B changes, the rate should be changing too, to the 1.56 power. But it's not because the thing is, hydroxide's there, and so the rate factors in the hydroxide. But as the crystal violet's being consumed, let's say we've consumed 90% of our crystal violet. After we've consumed 90% of our crystal violet, has B changed at all? No. And so even though B's impact is there, right, it doesn't change it And so overall, it's still first order because B is constant. Where you're going to see that is in the slope, K prime. Because K prime is going to factor in the hydroxide. So this is like the hydroxide to the 1.56 power. And so we see that here, and then in run 2, we look. B didn't change here, but the hydroxide initial was different. Since the hydroxide initial is different, the slope, the pseudo rate constant is different. And so we see it in the pseudo rate constant, the impact of hydroxide. We don't see it here because during the course of the reaction it didn't change. And so if I keep increasing the hydroxide, the pseudo rate constant is still going to go higher and higher, but it's still going to appear first order overall. It appears first overall because the hydroxide just didn't change to see it. So we'll see it, in other words, we're going to see it initially, depending on how high the concentration is. Because what we're going to see is this. So we have it now. It's going to equal K times the Cv plus to the first times the hydroxide to the 1.56. But what we did was we made the hydroxide so big that it stayed essentially constant over the course of this experiment. Since this whole thing stayed relatively constant, we called it a new rate constant, K prime. And so in other words, hydroxide doesn't change during the course of the experiment, so it's not going to have any impact on the rate. But hydroxide did change in going from run 1 to run 2, and therefore it's going to have an overall impact on the rate. That is, it's going to be just a bigger K prime. Run 2, we doubled the hydroxide. So we doubled the hydroxide, the impact was the rate tripled. It went 3 times as faster. And so we see that the impact of the hydroxide in the overall rate, but we see the behavior or the decay in the rate just due to the crystal violet. Does that make sense? Or not really? Kind of.
So is it because the crystal violet gets consumed a lot faster?
A lot faster. Yeah, during this time period, the hydroxide wasn't consumed at all, basically. And so let me just finish up by writing what we're after. We're after the whole rate law. So the rate is equal to K. The best K is going to be the average K value, which I calculated on this sheet here. The average K value came out to 26.41. The units are really weird because the rate always has to be in molar per time. So in this, it's molar per minute. You could have seconds, it's fine. But your K will be a little different if yours is in seconds. 26.41. Okay, the units on this are going to be molar to the minus 1.56, minutes to the minus 1. And that's because crystal violet will be in units of molar, but the hydroxide will be in units of molar to the 1.56. So we got to cancel that out so we can get molar per minute. And so this would be the rate law. The rate law just tells us, how the rate is impacted by the concentration. The integrated rate law tells us how much and how long. How much and how long. But the integrated rate law for multiple reactants like this is beyond the scope of 1B of this class, beyond the scope of this class. Okay, And so that's all. That's as far as we're going to get for this particular problem. Unfortunately, I have to leave early today because of appointment, so I have to skip out of my office half hour. But if you have questions, you can ask me tomorrow or make an appointment.